The Andromeda Galaxy is the closest large galaxy to our own galaxy, the Milky Way. When astronomers say major galaxy, they mean a huge galaxy filled with hundreds of billions or even trillions of stars. Andromeda is our nearest giant neighbor in the vast cosmic neighborhood we live in. To imagine how incredible this is, think about how many stars exist in a galaxy. Our Milky Way alone contains hundreds of billions of stars. Andromeda contains even more. Yet despite being the closest large galaxy to us, it is still unbelievably far away. If galaxies were cities in a gigantic universe-sized country, Andromeda would be the nearest major city to ours. Everything else nearby is much smaller, more like tiny towns compared to these enormous star-filled cities. Because it's so close on the cosmic scale, Andromeda is extremely important to astronomers. By studying it, scientists can learn how galaxies grow, evolve, and interact across billions of years. The Andromeda Galaxy contains around 1 trillion stars, which is an almost unimaginable number. For comparison, our own Milky Way galaxy is estimated to contain around 100 to 400 billion stars. That means Andromeda may have 2 to 5 times more stars than our galaxy. To understand how huge that number is, imagine counting 1 star every second without stopping. Even at that speed, it would take over 31,000 years just to count 1 trillion. Each of those stars could potentially have its own planets, moons, and entire solar systems. If many of those stars host planets like our Sun does, Andromeda might contain trillions of worlds. When you look at Andromeda through a telescope and see a soft glowing blur, that light is actually coming from the combined glow of about 1 trillion stars shining together. The Andromeda Galaxy was first recorded in the year 964 AD by a Persian astronomer named Abd al-Rahman al-Sufi. This was more than 1,000 years ago, long before telescopes were invented. Al-Sufi carefully studied the night sky and wrote about the objects he observed in a famous book called The Book of Fixed Stars. While observing the constellation Andromeda, he noticed a faint, misty patch of light that did not look like a normal star. Imagine spotting a tiny smudge in the night sky with nothing more than your eyes, not knowing it was actually an entire galaxy filled with hundreds of billions or even trillions of stars. At the time, no one knew what this mysterious object really was. But Al-Sufi's record became one of the earliest known descriptions of another galaxy, centuries before modern astronomy began. Before the discovery that Andromeda was a separate galaxy, many scientists believed the Milky Way was the entire universe. Every star visible in the night sky, every glowing cloud seen through telescopes, and every mysterious object astronomers observed was assumed to exist within our single galaxy. To people at that time, the Milky Way was thought to be the whole cosmic system, stretching as far as the universe possibly could. Imagine believing your hometown was the entire planet, with nothing beyond it. Then suddenly discovering that your town is just one city among millions across a vast world. That is similar to what happened in astronomy. When Andromeda was proven to be far outside the Milky Way, it revealed that our galaxy is only one island of stars in a much larger cosmic ocean, filled with countless other galaxies. The Andromeda Galaxy is classified as a barred spiral galaxy. This means it has a flat rotating disk with long spiral arms and a straight bar-shaped structure of stars running through its center. If you could view Andromeda from above, it would look a bit like a cosmic pinwheel. The spiral arms curve outward from the center, wrapping around the galaxy in huge sweeping patterns filled with stars, gas, and dust. The bar in the middle acts like a stellar highway, guiding gas and stars toward the galaxy's core. This movement helps fuel new star formation and shapes how the galaxy evolves over time. Our own Milky Way is also believed to be a barred spiral galaxy, which makes Andromeda somewhat like a giant cousin of our galaxy. In simple terms, Andromeda is a massive spinning disk of stars, with beautiful spiral arms stretching across space. Beyond the bright disk and spiral arms of the Andromeda Galaxy lies a huge, faint region called the galactic halo. This halo stretches far beyond the visible part of the galaxy, extending hundreds of thousands of light years into space. Unlike the bright disk filled with dense stars, the halo is much more spread out and mysterious. It contains scattered stars, ancient star clusters, and large amounts of invisible matter. To imagine its size, think of the visible galaxy as a bright island, while the halo is like a massive invisible ocean surrounding it. Most people only see the island, but the ocean around it is actually much larger. This halo also contains some of the oldest stars in the galaxy, acting like a cosmic record of Andromeda's past. By studying these stars, astronomers can learn how the galaxy grew and changed over billions of years. As we move forward, feel free to share where you're listening from, or leave a quick thought below. And if this channel means something to you, subscribing is a small way to support the journey. The Andromeda Galaxy shines with enormous luminosity, meaning it produces an incredible amount of light. This brightness comes from the combined glow of roughly 1 trillion stars spread across the galaxy. Each star shines on its own, just like our sun does. But when you gather trillions of stars together, their light adds up into something truly spectacular. Even from 2.5 million light years away, that combined light is strong enough for us to see Andromeda as a faint glowing patch in the night sky. Imagine a single light bulb in a dark field. It would be visible nearby. But if you placed 1 trillion light bulbs together, the glow would be visible from an enormous distance. That is essentially what Andromeda looks like from Earth, a vast ocean of starlight, where the brightness of countless stars blends together into one soft cosmic glow. When massive stars in the Andromeda Galaxy explode as supernovae, they do more than just release energy. These explosions actually create many of the heavy elements that exist in the universe. Inside normal stars, lighter elements like hydrogen and helium slowly fuse together to form heavier elements, such as carbon and oxygen. But the extremely violent conditions of a supernova allow even heavier elements to form, things like iron, gold, silver, and uranium. The explosion then blasts these newly formed elements into space, spreading them across the galaxy. Over time, this material becomes part of new stars, planets, and even future solar systems. In a way, supernovae act like cosmic recycling machines. The atoms that make up planets, and even our own bodies, were likely forged in explosions like these billions of years ago in galaxies such as Andromeda. At the very center of the Andromeda Galaxy lies a supermassive black hole. This is an incredibly dense object whose gravity is so strong that nothing, not even light, can escape once it gets too close. Black holes form when enormous amounts of mass are squeezed into a very small space. In the case of Andromeda, the central black hole is unbelievably powerful and sits deep inside the galaxy's bright core. Even though black holes themselves are invisible, astronomers can detect them by watching how nearby stars move. In Andromeda's center, stars orbit extremely fast, almost like cars racing around a tight circular track. The only explanation for this motion is the intense gravity of a massive black hole, pulling everything inward. Many large galaxies, including our own Milky Way, also contain supermassive black holes at their centers. At the center of the Andromeda Galaxy, astronomers discovered something unusual. 2 bright star clusters, sitting extremely close to each other near the galaxy's core. Most galaxies usually have just one concentrated cluster of stars at their center, so finding 2 was surprising. These clusters appear like 2 glowing knots of stars packed tightly together. At first, scientists thought Andromeda might have 2 separate galactic centers, which would have been very strange. A helpful way to imagine it is like seeing 2 bright city centers next to each other, instead of just one downtown area. Later studies revealed that these 2 clusters are actually part of a complex structure surrounding the supermassive black hole at the galaxy's core. Their unusual arrangement gave astronomers valuable clues about the powerful gravitational forces shaping the center of Andromeda. The Andromeda Galaxy is surrounded by more than 30 known satellite galaxies. These are much smaller galaxies that orbit around Andromeda due to its powerful gravitational pull. You can think of them like moons orbiting a giant planet, except on a much larger scale. Instead of a few moons like Earth has, Andromeda has dozens of small galaxies moving around it through space. Most of these satellite galaxies are dwarf galaxies, meaning they contain far fewer stars than Andromeda. While Andromeda holds about 1 trillion stars, some of these smaller galaxies may contain only a few million or a few billion stars. Over billions of years, gravity slowly pulls these satellites closer. Some will eventually merge with Andromeda, adding their stars to the giant galaxy and helping it grow even larger over time. Many of the dwarf galaxies orbiting the Andromeda Galaxy have slowly lost some of their stars because of Andromeda's powerful gravity. As these smaller galaxies move around the giant galaxy, strong gravitational forces can stretch and pull on them. This process is called tidal stripping. It works a bit like the moon's gravity pulling on Earth's oceans to create tides, but on a far larger scale. Instead of moving water, the gravity pulls entire stars away from the smaller galaxy. Over time, this can weaken the dwarf galaxy and scatter its stars across space. Some of those stars become part of Andromeda's outer halo. Imagine a small sandcastle slowly being washed apart by waves. In a similar way, the gravity of a giant galaxy can gradually pull apart smaller neighboring galaxies. A surprising fact about the Andromeda Galaxy is that most of its mass is actually invisible. The stars, gas, and dust we can see make up only a small part of the galaxy's total mass. Astronomers discovered this by studying how stars move inside Andromeda. The stars in the outer parts of the galaxy move much faster than expected, if only visible matter were present. Something else must be adding extra gravity. That hidden mass is believed to be dark matter, a mysterious substance that does not produce light and cannot be seen directly. To imagine this, think of watching leaves spinning quickly around an invisible whirlpool in water. Even if you cannot see the whirlpool itself, the motion of the leaves shows that something powerful is there. In Andromeda, this unseen mass actually makes up most of the galaxy. Dark matter also plays a major role in how the Andromeda Galaxy rotates. When astronomers measure the speed of stars in the galaxy, they notice something surprising. Stars far from the center of Andromeda move almost as fast as stars closer to the center. According to normal gravity from visible matter alone, those outer stars should move much slower. Instead, they race around the galaxy at very high speeds. It's similar to watching a spinning carousel, where the outer seats somehow move just as fast as the inner ones. Normally, that shouldn't happen. The explanation is that a large amount of invisible mass, dark matter, is spread throughout and around the galaxy. This hidden mass provides the extra gravity needed to keep those outer stars moving so quickly without flying off into space. The Andromeda Galaxy and the Milky Way are on a slow collision course through space. Instead of moving away from each other like most galaxies in the expanding universe, these two giant galaxies are gradually drifting closer together because of their strong gravitational pull. Right now, they are about 2.5 million light-years apart, but the distance between them is slowly shrinking. Over billions of years, gravity will continue pulling them toward each other. You can imagine two massive whirlpools in a huge ocean slowly drifting closer until they eventually meet and merge. Even though galaxies contain enormous numbers of stars, they are also mostly empty space. So when this future collision happens, it will not be like two solid objects crashing together. Instead, the galaxies will slowly interact, stretch, and merge over a very long time. The merger between the Andromeda Galaxy and the Milky Way will not happen quickly. Instead, The entire process will unfold over billions of years. When the galaxies first pass close to each other, gravity will stretch their spiral arms and pull huge streams of stars and gas outward. After that first encounter, the galaxies will drift apart again before gravity slowly pulls them back together. This cycle may repeat several times. Each pass mixes more stars and gas until the two galaxies gradually combine into one larger system. You can imagine it like two giant whirlpools in the ocean, slowly circling each other, coming close, drifting apart, and then meeting again until they finally merge. Because galaxies are so enormous and mostly empty space, this slow cosmic dance takes an incredibly long time to fully complete. As the Andromeda Galaxy slowly moves closer to the Milky Way, it will appear larger and larger in our night sky over millions of years. Right now, Andromeda looks like a small, faint smudge of light, even though it is actually enormous. That's because it is still about 2.5 million light years away, but as the distance slowly shrinks, the galaxy will gradually take up more space in the sky. You can imagine this like watching a distant mountain while traveling toward it. At first it looks small on the horizon, but as you get closer, it begins to dominate your view. Over millions of years, Andromeda's bright core and long spiral arms will become easier to see. Future observers on Earth, or wherever humanity might be, could witness a slowly growing galaxy stretching across the sky. As the Andromeda Galaxy approaches the Milky Way, the appearance of the night sky will change dramatically over millions and billions of years. Today, the sky we see is mostly filled with stars from our own galaxy, along with a faint band of light known as the Milky Way stretching across the sky. But as Andromeda gets closer, it will gradually become one of the most noticeable objects in the sky. Its bright central region and vast disk of stars will grow larger and brighter over time. Eventually, huge regions of the sky could glow with the light of another galaxy, slowly moving closer. Imagine looking up and seeing an enormous swirling galaxy slowly expanding across the heavens, with bright clusters and glowing clouds visible to the naked eye. For future observers, the sky will transform into a spectacular cosmic panorama, unlike anything we see today. When the Andromeda Galaxy and the Milky Way begin merging, huge clouds of gas inside both galaxies will collide with each other. Unlike stars, which are usually very far apart, gas clouds are large and spread out, making collisions much more likely. These clouds can stretch across dozens or even hundreds of light years. When two such clouds crash together, the gas becomes compressed and heated. Imagine two massive weather systems colliding in the sky. As the clouds crash together, the air gets pushed and squeezed. In galaxies, something similar happens when gas clouds meet. This compression is very important because it can trigger the formation of new stars. The squeezed gas begins collapsing under gravity, eventually becoming dense enough for new stars to ignite. So while the galaxies merge, their colliding gas clouds will help create entire new generations of stars. As the Andromeda Galaxy and the Milky Way interact, their shapes will begin to stretch into enormous structures called tidal tails. These are long streams of stars, gas and dust that are pulled outward by powerful gravitational forces. When two large galaxies pass close to each other, gravity does not pull evenly on every part of them. Some regions are tugged more strongly than others, stretching material far into space. Imagine pulling apart a ball of soft taffy. As you stretch it, long strands form between your hands. In a similar way, gravity stretches parts of the galaxies into huge glowing tails. These tidal tails can extend hundreds of thousands of light years across space. They become some of the most dramatic visual features during a galaxy merger, showing how strongly gravity can reshape entire galaxies. When the Andromeda Galaxy and the Milky Way merge, their two supermassive black holes will eventually begin to spiral toward each other near the center of the newly forming galaxy. At first, each black hole will still sit at the center of its original galaxy. But as the galaxies combine, Gravity will slowly pull the black holes closer together. Over time, they will begin orbiting each other in a huge cosmic spiral. You can imagine two massive whirlpools in water, slowly circling one another, before finally merging into one. Each of these black holes is incredibly massive. The Milky Way's black hole contains about 4 million suns, while Andromeda's holds roughly 100 million suns. Together they will form an extraordinary system. This slow spiral toward each other will take millions of years, marking the beginning of one of the most powerful events in the future history of our cosmic neighborhood. The powerful gravitational waves created when the supermassive black holes of the Andromeda Galaxy and the Milky Way merge could be detectable across enormous distances in the universe. Even though gravitational waves become weaker as they travel, an event involving such massive black holes would send out an incredibly strong signal. The waves could travel for millions or even billions of light years, carrying information about the collision. Scientists today already have instruments designed to detect gravitational waves, such as extremely sensitive observatories that measure tiny changes in distance smaller than the width of an atom. You can imagine these detectors like cosmic microphones, listening for faint vibrations traveling through space-time. Future civilizations with advanced technology might be able to detect the waves from this enormous black hole merger and learn exactly when and how the two galaxies' central black holes finally combined. Long before its future collision with the Milky Way, the Andromeda Galaxy has already absorbed several smaller galaxies during its long history. Galaxies grow over billions of years, partly by merging with smaller neighbors. When a dwarf galaxy gets too close to a giant galaxy like Andromeda, gravity begins pulling it apart. Its stars slowly spread out and eventually become part of the larger galaxy. You can imagine this process like a large river absorbing smaller streams. Over time, the water from the smaller streams blends completely into the main river. Evidence of these past mergers still exists today. Astronomers can detect faint streams of stars and unusual star motions that reveal where smaller galaxies were torn apart and absorbed. These ancient mergers helped Andromeda grow into the massive galaxy we see today. Astronomers believe the Andromeda Galaxy likely consumed several dwarf galaxies long ago, especially during the early stages of its formation. In the young universe, galaxies were much smaller and closer together, which made collisions and mergers much more common. When a dwarf galaxy drifted too close to Andromeda, its stars would slowly be pulled apart by the giant galaxy's gravity. Over time, the smaller galaxy would lose its structure and eventually disappear as its stars became part of Andromeda. You can imagine a large whirlpool in water, pulling in smaller swirling currents. The smaller currents eventually blend completely into the larger one. Even though those dwarf galaxies are gone, they left behind clues. Streams of stars and unusual star motion still show astronomers where these ancient galaxies once existed, before being absorbed into Andromeda. The Andromeda Galaxy and the Milky Way are the two largest galaxies in a small cosmic neighborhood called the Local Group. This group is a collection of galaxies that are all connected by gravity and slowly moving through space together. Although the Local Group contains more than 50 galaxies, most of them are tiny dwarf galaxies with far fewer stars. Andromeda and the Milky Way are the true giants of this region, containing the vast majority of the stars in the entire group. You can imagine the Local Group like a small town dominated by two huge cities, with many smaller villages scattered around them. Because of their enormous size and gravity, Andromeda and the Milky Way strongly influence the movement of the smaller galaxies nearby. Over billions of years, their gravitational pull helps shape the entire structure of the Local Group. The Milky Way is also slowly absorbing smaller dwarf galaxies, just like the Andromeda Galaxy does. Galaxy growth through mergers is a normal process across the universe. Several dwarf galaxies already orbit our galaxy, and some of them are gradually being pulled apart by the Milky Way's gravity. As their stars spread out, they form long stellar streams that slowly mix into the larger galaxy. You can imagine this process like small rivers merging into a larger river system. Over time, the smaller streams lose their separate identity and become part of the bigger flow. This means our galaxy is still growing and changing today, even though the process happens extremely slowly. One well-known example is a dwarf galaxy currently being torn apart by the Milky Way, showing that galaxy mergers are still happening right now. Astronomers have detected many X-ray sources inside the Andromeda Galaxy. X-rays are a very energetic form of light that cannot be seen by human eyes, but can be detected by special space telescopes. These X-rays usually come from extremely hot and energetic objects. In galaxies like Andromeda, many X-ray sources are created when material falls onto very dense objects, such as neutron stars or black holes. As gas from nearby stars spirals inward, it becomes extremely hot, sometimes reaching millions of degrees. At those temperatures, the gas begins to emit powerful X-rays. You can imagine this like metal glowing when it becomes very hot. Except the temperatures involved in these cosmic systems are far beyond anything found on Earth. By studying these X-ray signals, astronomers can discover hidden objects inside Andromeda that would otherwise be invisible in normal light. The central region of the Andromeda Galaxy may produce energetic jets of particles and radiation shooting outward from near its supermassive black hole. When gas falls toward a black hole, it doesn't always disappear immediately. Instead, the gas forms a rapidly spinning disk around the black hole. In some cases, powerful magnetic forces in this disk can launch narrow beams of particles outward at extremely high speeds. These beams are called jets, and they can travel vast distances through space. Some galactic jets stretch thousands or even millions of light years long. You can imagine a cosmic fire hose blasting material outward from the galaxy's center. Although Andromeda's central black hole is currently fairly quiet compared to some active galaxies, scientists believe it may have produced energetic activity in the past, leaving traces that astronomers continue to study. Scientists believe the Andromeda Galaxy may contain trillions of planets. Since the galaxy holds around 1 trillion stars, and many stars are known to have planetary systems, the number of possible planets could be enormous. In our own Milky Way, astronomers have already discovered thousands of exoplanets orbiting distant stars. These discoveries suggest that planets are very common throughout the universe. If even a fraction of Andromeda's stars have planets, that would still mean billions or trillions of worlds scattered across the galaxy. To imagine the scale, picture a galaxy filled with stars like our Sun, each surrounded by its own family of planets, some rocky like Earth, others massive gas giants like Jupiter. Among these countless worlds, some could have oceans, atmospheres, or even conditions suitable for life, making Andromeda a vast collection of possible planetary systems. Some planets in the Andromeda Galaxy are likely gas giants, similar to Jupiter and Saturn in our own solar system. These planets are enormous and made mostly of gas rather than solid rock. Gas giants can be many times larger than Earth. Jupiter, for example, is so big that more than 1,300 Earths could fit inside it. Planets like this may exist around many stars in Andromeda as well. These giant planets often have thick atmospheres made of hydrogen and helium, along with powerful storms and strong winds. Some gas giants discovered in other star systems orbit extremely close to their stars and can become hotter than molten lava. Even though gas giants themselves are unlikely to support life, they may have large moons orbiting them. Some of those moons could potentially have oceans or atmospheres. The light you see from the Andromeda Galaxy tonight began its journey about 2.5 million years ago. That means the faint glow reaching your eyes left that galaxy long before modern humans existed. To understand this, imagine turning on a flashlight in another galaxy and waiting for the light to arrive on Earth. Because space is so vast, that light would travel for millions of years before reaching us. Around 2.5 million years ago, when this light first started its trip toward Earth, early human ancestors were only beginning to walk upright and use simple stone tools. Mammoths and saber-toothed cats still roamed the planet. So when you look at Andromeda in the night sky, you are not seeing it as it is today. You are seeing a cosmic photograph from the distant past, a snapshot from a time when humanity itself was just beginning its story. The Andromeda Galaxy is roughly twice the diameter of our Milky Way galaxy, while the Milky Way stretches about 100,000 to 120,000 light-years across. Andromeda spreads out to around 220,000 light-years from one side to the other. That means if our galaxy were the size of a large city, Andromeda would be more like an entire large country by comparison. It is simply on a much bigger scale. Because of this enormous size, Andromeda has more space to hold stars, gas clouds, star clusters, and dark matter. Its spiral arms stretch far into space, forming a gigantic rotating disk filled with cosmic activity. Despite being so huge, Andromeda still looks like only a faint smudge in the night sky from Earth. That's because it is millions of light years away, making even this massive galaxy appear small from our distant viewpoint. For many centuries, astronomers believed the Andromeda Galaxy was simply a nebula inside the Milky Way. A nebula is a cloud of gas and dust in space where stars can form, and early telescopes showed Andromeda as nothing more than a faint glowing blur. Because it looked cloudy and had no clear shape, scientists assumed it was just another gas cloud floating somewhere within our own galaxy. In fact, many objects in the sky were once called spiral nebulae because they looked like fuzzy spirals through early telescopes. Imagine seeing a distant city at night from hundreds of kilometers away. The lights might blur together and look like a glowing fog. That's similar to how Andromeda appeared. It took centuries before astronomers realized this nebula was not a cloud at all, but an entire galaxy far beyond our own. One of the most amazing things about the Andromeda Galaxy is that you can actually see it without a telescope if the sky is dark enough. On a clear night, far away from city lights, Andromeda appears as a very faint, misty glow in the sky. Even though it is 2.5 million light-years away, its enormous size and the combined light of around 1 trillion stars make it just bright enough to be visible to human eyes. However, it doesn't look like a galaxy when you see it. Instead, it appears as a small, blurry patch, almost like a tiny smudge of light. To understand how incredible this is, imagine looking across a distance so vast that light itself takes 2.5 million years to travel. Yet your eyes can still detect that faint glow from billions upon billions of stars. It's one of the most distant objects humans can see without any equipment. The disk of the Andromeda Galaxy is tilted about 77 degrees relative to our view from Earth. This means we are not looking at the galaxy straight from above or perfectly from the side. Instead, we see it at an angle. Imagine holding a large dinner plate in front of you. If you tilt the plate slightly, you can still see its circular shape, but it starts to look stretched into an oval. That's very similar to how Andromeda appears in the sky. Because of this tilt, the galaxy's spiral structure is harder to see with the naked eye. Through telescopes, however, astronomers can still observe the disk, the glowing center, and the dusty spiral arms. This angled view actually helps scientists study how stars move inside the galaxy, because they can see how different parts of the disk rotate across space. The Andromeda Galaxy contains hundreds of globular clusters, which are dense, spherical groups of stars tightly packed together by gravity. Each globular cluster can contain hundreds of thousands or even millions of stars gathered into a single glowing ball. If you could travel near one of these clusters, the sky would look completely different from what we see on Earth. Instead of a few bright stars scattered across the night, you might see thousands of stars shining closely together, lighting up the sky from every direction. These clusters are extremely old and stable. Many of them formed during the early history of the galaxy and have been orbiting Andromeda for billions of years. To picture one, imagine a giant glowing swarm of fireflies packed into a sphere, all held together by gravity and drifting through space far out in the galaxy's halo. The spiral arms of the Andromeda Galaxy are home to many massive young stars that formed relatively recently in cosmic terms. These stars are much larger and hotter than our Sun, and they shine with an intense blue or white light. Some of these stars can be 10 to 50 times more massive than the Sun. Because of their huge size, they burn through their fuel extremely fast. While our Sun will live for about 10 billion years, some massive stars may only live a few million years before they explode as supernovae. Imagine a fire that burns incredibly bright, but quickly runs out of fuel. That's similar to how these giant stars behave. These young stars often form in clusters within glowing gas clouds in the spiral arms, turning those regions into brilliant, energetic parts of the galaxy filled with newborn starlight. Inside the Andromeda Galaxy, astronomers have discovered some stars that are among the largest known in the universe. These stars are true giants, many times larger than our Sun. Some of them are called supergiants, and they can grow to hundreds of times the Sun's diameter. If one of these massive stars replaced our Sun at the center of the solar system, its surface could stretch past the orbit of Mars or even Jupiter. Despite their enormous size, these stars usually live short and dramatic lives. Because they burn through their fuel very quickly, they shine extremely bright, but often last only a few million years before collapsing or exploding as supernovae. These giant stars act like cosmic beacons, lighting up huge areas of the galaxy and helping astronomers study distant regions of Andromeda. The supermassive black hole at the center of the Andromeda Galaxy is over 25 times more massive than the black hole at the center of our Milky Way. Our galaxy's central black hole, known as Sagittarius A, has a mass of about 4 million suns. In comparison, Andromeda's central black hole contains about 100 million suns worth of mass. To imagine the difference, think of two objects, one the size of a basketball, and another the size of a small car. Both are massive, but one clearly dominates in size and power. Because Andromeda's black hole is so much larger, its gravitational influence in the galaxy's center is much stronger. It plays a major role in shaping the movement of stars and gas in that region, acting like a powerful gravitational engine at the heart of the galaxy. The unusual movement of the star clusters near the center of the Andromeda Galaxy helped astronomers detect a hidden supermassive black hole. Since black holes cannot be seen directly, scientists must look for clues in how nearby objects behave. When astronomers carefully observed the stars near Andromeda's center, they noticed something strange. The stars were moving incredibly fast and in unusual paths, much faster than they should if only normal stars were pulling on them. It was similar to seeing leaves spinning rapidly around an invisible whirlpool in water. Even if you cannot see the whirlpool itself, the motion of the leaves reveals that something powerful is pulling them. By studying these extreme star movements, scientists realized that the only explanation was a massive black hole hidden at the galaxy's center. One of the most well-known satellite galaxies orbiting the Andromeda Galaxy is called M32. It is a small dwarf galaxy that stays very close to Andromeda compared to many of the other satellites. Even though M32 is tiny compared to Andromeda, it is still enormous by everyday standards. It contains billions of stars, all packed into a relatively small region of space. If our solar system were located inside M32, the night sky would likely appear much brighter and more crowded with stars than what we see from Earth. Astronomers believe M32 may have once been a larger galaxy that was slowly stripped of its outer stars by Andromeda's powerful gravity. In a way, M32 is like a small companion galaxy that has spent billions of years orbiting a much larger cosmic neighbor. The powerful gravity of the Andromeda Galaxy can distort the shapes of the smaller galaxies that orbit around it. These distortions happen because of something called tidal forces, which occur when gravity pulls more strongly on one side of an object than the other. A simple way to imagine this is by thinking about how the moon pulls on Earth's oceans, creating ocean tides. But on the scale of galaxies, these forces can stretch entire galaxies instead of just water. As a dwarf galaxy moves around Andromeda, the side closer to the giant galaxy feels a stronger pull. Over time, this uneven gravity can stretch the small galaxy into long, thin shapes, pulling stars away from it. Some satellite galaxies end up looking elongated or warped, showing clear signs that Andromeda's powerful gravity is slowly reshaping them. The dark matter in the Andromeda Galaxy is not spread evenly throughout the galaxy. Instead, it forms a huge halo that surrounds the entire galaxy, extending far beyond the visible stars and spiral arms. This halo is enormous, while the bright disk of Andromeda stretches about 220,000 light-years across. The dark matter halo may extend hundreds of thousands or even over 1,000,000 light-years outward. Imagine a bright island surrounded by a massive invisible ocean. The stars and gas form the island we can see, while the dark matter halo is the vast ocean surrounding it. Even though we cannot see this halo directly, its gravity holds the galaxy together and influences the motion of stars, gas clouds, and even nearby satellite galaxies. In many ways, the visible galaxy is just the bright center of a much larger, invisible structure. The strange speeds of stars in galaxies like the Andromeda Galaxy helped scientists realize that dark matter must exist. When astronomers carefully measured how fast stars move at different distances from the center, the results didn't match what normal gravity predicted. If only visible matter were present, stars farther out should slow down as their distance increases. Instead, stars in the outer regions kept moving almost just as fast as those near the center. It was like watching cars drive around a racetrack, where the outer lanes somehow move just as fast as the inner lanes, even though they travel a much larger circle. The only explanation was that a huge amount of invisible mass was spread throughout the galaxy, providing extra gravity. This discovery became one of the key pieces of evidence that dark matter dominates the mass of galaxies. When the Andromeda Galaxy and the Milky Way begin their long approach, the very first parts to interact will not be the visible stars or spiral arms. Instead, their enormous dark matter halos will meet first. Each galaxy is surrounded by a vast halo of invisible dark matter that stretches hundreds of thousands of light-years beyond the visible disk. These halos are far larger than the bright galaxies we see in pictures. As the galaxies drift closer together, these invisible halos will begin to overlap and interact long before the stars do. It's similar to two large clouds slowly touching before the objects inside them ever meet. This early interaction will start changing the motion of stars, gas, and smaller satellite galaxies, setting the stage for the slow cosmic dance that will eventually lead to the full merger of the two giant galaxies. When the Andromeda Galaxy and the Milky Way begin merging, their huge clouds of gas will start colliding and compressing together. This process will trigger an intense period of star formation, sometimes called a starburst. Normally, stars form slowly inside galaxies, but during a merger, gas clouds can be squeezed tightly by gravity and collisions. When that happens, new stars can form much faster than usual. You can imagine squeezing a sponge full of water. As pressure builds, everything inside gets pushed together. In galaxies, this pressure forces gas clouds to collapse and ignite new stars. During this time, the merging galaxies could produce large numbers of bright, young stars, lighting up vast regions of space. The sky in parts of the galaxy may glow with clusters of newly formed blue stars shining brilliantly across the merging system. As the Andromeda Galaxy moves closer to the Milky Way, it will eventually appear so large that it could stretch across a huge portion of the night sky. Right now, Andromeda looks tiny, because of the enormous distance between our galaxies. But as the gap slowly shrinks over millions and billions of years, the galaxy's full size will become easier to see. Andromeda is about 220,000 light-years wide, which is more than twice the width of the Milky Way. As it approaches, that enormous structure will slowly fill more of the sky. Imagine watching a distant storm cloud slowly moving closer. At first it appears small, but as it approaches, it spreads across more and more of the horizon. In the far future, Andromeda could appear as a huge glowing structure of stars, stretching across a large part of the sky. As the Andromeda Galaxy and the Milky Way begin pulling on each other, gravity will stretch groups of stars into long structures known as stellar streams. These streams are like cosmic rivers of stars flowing across space. When the strong gravitational forces of two large galaxies interact, they can pull stars out from their original orbits and stretch them into thin, glowing trails. Some of these streams may extend tens or even hundreds of thousands of light years across space. They will slowly arc around the merging galaxies, marking the paths that stars once followed. Imagine pulling apart a ball of soft dough and watching it stretch into long strands. Stellar streams form in a somewhat similar way as gravity pulls stars outward. These glowing trails will become clear signs of the ongoing merger between the two giant galaxies. During the intense star formation triggered by the merging of the Andromeda Galaxy and the Milky Way, many bright blue stars will form. These stars are among the hottest and most energetic stars in the universe. Blue stars are usually much larger than our Sun, sometimes containing many times its mass. Because of their enormous size, they burn their fuel extremely quickly and shine with a brilliant blue-white light. You can imagine them like cosmic spotlights, lighting up huge regions of space around them. Even though they are incredibly bright, these stars live relatively short lives. While the Sun will shine for about 10 billion years, some massive blue stars may only live a few million years before exploding as supernovae. During the galaxy merger, these brilliant stars will make parts of the merging galaxies glow with intense blue light. During the violent gravitational interactions between the Andromeda Galaxy and the Milky Way, some stars will be flung completely out of the merging galaxies and sent drifting into intergalactic space. As the two galaxies pull strongly on each other, stars can be caught in complex gravitational forces. Some of them may gain enough speed to escape the combined gravity of both galaxies. You can imagine this like a slingshot effect. When an object swings around something very massive, it can suddenly be thrown outward at high speed. These runaway stars may travel far beyond the galaxies, entering the vast emptiness between galaxies. Once there, they will drift alone through space, surrounded by darkness and distant galaxies. Even though this sounds dramatic, only a small fraction of stars will be ejected this way during the merger. After orbiting each other for millions of years, the two supermassive black holes from the Andromeda Galaxy and the Milky Way will eventually merge into a single, even larger black hole. As the black holes spiral closer together, their gravitational pull becomes stronger and stronger. Their orbit shrinks until they finally collide and combine. This event will be one of the most powerful mergers in the universe. When the black holes finally join, an enormous amount of energy will be released in the form of gravitational waves, ripples that travel through space itself. To imagine the scale, think about two objects, each containing millions or even hundreds of millions of suns worth of mass, crashing together. Although this event will be incredibly energetic, it will still occur far away from most stars, meaning the rest of the galaxy will continue orbiting around the newly formed supermassive black hole. After the supermassive black holes of the Andromeda Galaxy and the Milky Way merge, the new black hole could become one of the largest black holes in the entire local group of galaxies. The local group is the small collection of galaxies that includes Andromeda, the Milky Way, and dozens of smaller galaxies around them. Most of those galaxies are tiny compared to these two giants, and their central black holes, if they have them at all, are much smaller because Andromeda's black hole is already extremely massive. The merged black hole will dominate the gravitational center of the newly formed galaxy. Imagine combining the largest engines from two huge ships into a single machine. The result becomes the most powerful engine in the entire fleet. This giant black hole will sit at the heart of the merged galaxy, quietly shaping the motion of stars for billions of years. The halo of the Andromeda Galaxy contains a large amount of debris left behind from ancient galaxy collisions. This debris includes stars, gas, and star clusters that once belonged to smaller galaxies that Andromeda absorbed long ago. When a dwarf galaxy gets pulled apart by Andromeda's gravity, its stars do not disappear. Instead, they spread out across the halo of the larger galaxy. Over time, these stars form faint structures such as stellar streams, arcs, and scattered star groups. You can imagine this like the remains of waves after two ocean currents collide, leaving swirling patterns behind. Some of these remnants are extremely old, dating back billions of years. By studying them, astronomers can trace the history of past mergers and learn how Andromeda gradually grew by consuming smaller galaxies over cosmic time. The enormous size of the Andromeda Galaxy is largely the result of many past mergers with smaller galaxies. Over billions of years, each collision added more stars, gas, dust, and dark matter to the growing galaxy. Every time Andromeda absorbed a dwarf galaxy, it gained millions or even billions of additional stars. Slowly, these additions helped build the massive galaxy we see today, which now contains around 1 trillion stars. You can think of this process like building a large snowball. As the snowball rolls through the snow, it collects more material and becomes bigger and heavier. In the same way, Andromeda gradually grew larger by gathering smaller galaxies over cosmic time. These ancient mergers played a huge role in shaping its spiral arms, halo, and enormous mass. Although the local group contains more than 50 galaxies, the vast majority of them are dwarf galaxies. These are much smaller galaxies compared to giants like the Andromeda Galaxy or the Milky Way. While Andromeda holds about 1 trillion stars, many dwarf galaxies contain only a few million to a few billion stars. That may still sound enormous, but in galactic terms it is very small. You can imagine the difference like comparing a small village to a massive megacity. The dwarf galaxies are the villages, while Andromeda and the Milky Way are the giant cities dominating the region. Because dwarf galaxies are smaller, they are also more vulnerable to the gravity of larger galaxies. Over billions of years, many of them may eventually be pulled apart or absorbed by the larger galaxies nearby. The local group, the region of space that includes the Andromeda Galaxy, the Milky Way, and dozens of smaller galaxies, spans about 10 million light-years across. A light-year is the distance light travels in 1 year, moving at about 300,000 kilometers per second. So when astronomers say the local group is 10 million light-years wide, they are describing an enormous region of space. To imagine this scale, even light, the fastest thing in the universe, would take 10 million years to travel from one side of the local group to the other. Within this vast region, galaxies slowly move under the influence of gravity. Some orbit the larger galaxies, while others drift through space along slow cosmic paths. Despite this huge size, the local group is only a tiny part of the much larger universe, filled with countless other galaxy groups and clusters. Some of the intense X-ray sources inside the Andromeda Galaxy are created by stellar black holes. These are black holes formed when massive stars collapse at the end of their lives. Unlike the supermassive black hole in the center of the galaxy, stellar black holes are much smaller. They usually contain a few to dozens of times the mass of the Sun, but even at this size, their gravity is extremely powerful. In certain star systems, a black hole orbits a normal star, the black hole's gravity can pull gas from its companion star. As this gas spirals toward the black hole, it forms a hot, glowing disk of material. The gas becomes so hot that it emits powerful X-rays, which astronomers can detect from millions of light years away. These systems act like cosmic lighthouses, revealing the presence of otherwise invisible black holes inside Andromeda. Some of the large gas clouds inside the Andromeda Galaxy glow brightly when observed in ultraviolet light. Ultraviolet light is a form of radiation that has more energy than visible light, but it cannot be seen by human eyes without special instruments. These glowing clouds are usually located near young, hot stars. Massive young stars release enormous amounts of energy, including ultraviolet radiation. This radiation excites the surrounding gas, causing it to shine. You can imagine this like a neon sign lighting up when electricity flows through the gas inside it. In galaxies, the energy from young stars acts like that electricity, making nearby gas clouds glow. Space telescopes that can detect ultraviolet light allow astronomers to spot these active regions, revealing where new stars are currently forming inside Andromeda. One technique that has hinted at the presence of planets in the Andromeda Galaxy is called gravitational microlensing. This method takes advantage of gravity's ability to bend light. When a star passes directly in front of another distant star, the gravity of the closest star can act like a natural magnifying glass. It briefly bends and amplifies the light from the background star, making it appear brighter for a short time. If the foreground star has a planet orbiting it, that planet can slightly change the pattern of the brightening. Astronomers can detect this tiny change and infer that a planet may be present. You can imagine it like a small ripple appearing on a larger wave, revealing that something small passed through it. Using this technique, scientists have found hints that planets may exist even in galaxies as distant as Andromeda. Some planetary systems in the Andromeda Galaxy may look very similar to our own solar system. Around certain stars, planets might orbit at different distances, forming a family of worlds with rocky inner planets and larger gas giants farther out. In our solar system, small rocky planets like Mercury, Venus, Earth, and Mars orbit closer to the Sun, while giant planets like Jupiter and Saturn exist much farther away. Astronomers have already discovered many similar arrangements around stars in the Milky Way. There is a good chance that the same patterns occur in Andromeda as well. You can imagine distant stars in Andromeda with their own planetary families, where planets circle their star for billions of years, just like the planets around our Sun. Some of those systems may contain multiple planets, moons, asteroid belts, and comets, forming complex planetary environments. The Andromeda Galaxy is the largest galaxy in our local cosmic neighborhood, a region of space called the local group. This group contains more than 50 galaxies held together by gravity, but most of them are small dwarf galaxies. Andromeda stands out as the true giant of this group. It contains an enormous number of stars and stretches across an incredible distance of space. If the local group were like a small neighborhood of houses, Andromeda would be the largest mansion on the block. Our own galaxy, the Milky Way, is also very large, but current evidence suggests Andromeda may be even more massive overall. Together, these two giant galaxies dominate the entire local group. Everything else nearby, dozens of smaller galaxies, are like tiny satellites orbiting these two cosmic giants, slowly moving through space under their powerful gravitational pull. The Andromeda Galaxy is racing toward the Milky Way at about 110 kilometers per second. That may sound like just a number, but it's an astonishing speed when you compare it to everyday motion. At 110 kilometers per second, Andromeda is moving about 396,000 kilometers per hour. That's fast enough to circle the entire Earth almost 10 times in a single hour. A commercial airplane, by comparison, travels only around 900 kilometers per hour, which means Andromeda is moving over 400 times faster than a jet airliner. Even at this incredible speed, the galaxies will not collide anytime soon because the distance between them is so enormous. It will still take about 4 billion years before they begin to seriously interact. But every second, minute, and year that passes, Andromeda is quietly getting closer. When astronomers confirmed that the Andromeda Galaxy was a separate galaxy, it dramatically changed our understanding of the universe. Before this discovery, scientists believed the Milky Way was the entire universe. Everything they could see, every star, nebula, and glowing cloud, was thought to exist inside one giant galaxy. But Andromeda proved something astonishing. If it was a separate galaxy millions of light years away, then the universe must contain many other galaxies too. Imagine believing your entire life that your city was the whole world, only to discover there are millions of other cities spread across a vast planet. That is essentially what happened to astronomy. The universe suddenly became far larger than anyone had imagined, filled with countless galaxies scattered across unimaginable distances. And all of that realization began with the discovery that Andromeda was not part of our galaxy. The Andromeda Galaxy is the most distant object that most people can see with their naked eyes. That means you can look up at the night sky and directly see something that is 2.5 million light years away without using any telescope or binoculars. To understand how incredible this is, imagine spotting a glowing object so far away that the light reaching your eyes began its journey long before modern humans existed. Most things we see in the night sky, like stars, are much closer. Even bright stars are usually only tens or hundreds of light years away. Andromeda is millions of light years away, yet its enormous size and the light of around 1 trillion stars combined make it just visible under dark skies. In simple terms, when you see Andromeda, you are looking farther into space than with almost anything else your eyes can detect. While the center of the Andromeda Galaxy contains mostly very old stars, its spiral arms are filled with younger, hotter stars. These stars formed much more recently from large clouds of gas and dust scattered throughout the galaxy's disk. Young stars are often bright blue or white, and they burn extremely hot compared to older stars like our Sun. Because of their intense heat and energy, they shine very brightly and help light up the spiral arms of the galaxy. You can imagine the spiral arms as busy construction zones of the galaxy, where new stars are constantly being created. Huge clouds of gas collapse under gravity, forming clusters of newborn stars that glow intensely. However, these young stars usually live shorter lives. Some may burn through their fuel in only a few million years, compared to the Sun's lifespan of about 10 billion years. The Andromeda Galaxy contains enormous clouds of gas and dust drifting throughout its spiral arms. These clouds are some of the most important ingredients for creating new stars. Many of these clouds are incredibly large. Some stretch across hundreds of light years, meaning light itself would take hundreds of years just to travel from one side of the cloud to the other. Inside these vast clouds, gravity slowly pulls gas and dust together. As the material gathers, it becomes denser and hotter until new stars begin to form. You can think of these clouds as giant cosmic factories, where stars are constantly being produced. If one of these clouds were placed where our solar system is, it would stretch far beyond the orbit of Pluto, many times over. Hidden inside these dark regions are future stars that will shine for billions of years. The Andromeda Galaxy experiences supernova explosions on a regular basis. A supernova happens when a massive star reaches the end of its life and explodes with incredible power. These explosions are among the most energetic events in the universe. For a short time, a single supernova can shine brighter than billions of stars combined. Imagine one star suddenly becoming as bright as an entire galaxy. That's how powerful these events can be. When a star explodes, it blasts enormous amounts of energy and material into space. The explosion can send shockwaves racing across nearby gas clouds and illuminate huge regions of the galaxy. From Earth, astronomers occasionally detect these supernovae in Andromeda through powerful telescopes. Even from 2.5 million light-years away, these explosions can still be visible because of how incredibly bright they become. The Andromeda Galaxy contains a complex mix of different types of stars, known as stellar populations. This means the galaxy is not filled with just one kind of star. Instead, it contains stars of many ages, sizes, colors, and stages of life. Some stars are ancient, formed more than 10 billion years ago when the galaxy was still young. Others are middle-aged, like our Sun, and many are very young, only a few million years old, and still shining brightly in the spiral arms. You can imagine the galaxy like a massive city, with people of every generation, children, adults, and elders all living together. In the same way, Andromeda holds multiple generations of stars that formed at different times throughout its long history. By studying these different stellar populations, astronomers can piece together how the galaxy grew and evolved over billions of years. The supermassive black hole at the center of the Andromeda Galaxy has such powerful gravity that it controls how nearby stars move. Stars close to the center are pulled into extremely fast orbits around this invisible object. Some of these stars move at hundreds of kilometers per second, racing through space much faster than most stars in the outer parts of the galaxy. It's similar to how planets in our solar system move faster when they are closer to the sun. Imagine a powerful whirlpool in water. Objects near the edge move slowly, but anything close to the center spins around extremely fast. The black hole acts like that cosmic whirlpool, pulling nearby stars into tight, rapid paths. By carefully measuring these fast-moving stars, astronomers were able to calculate the mass of the hidden black hole lurking in Andromeda's core. One day in the distant future, the supermassive black hole in the Andromeda Galaxy may merge with the black hole at the center of the Milky Way. This will happen when the two galaxies collide and slowly combine into a single, much larger galaxy. At first, the two black holes will orbit each other like two massive dancers circling on a cosmic stage. Over time, gravity will pull them closer and closer together. Eventually, they will collide and merge into an even larger supermassive black hole. When this happens, the event will release powerful gravitational waves, which are ripples that travel through space itself. Even though the black holes are incredibly massive, this process will take millions of years to fully complete. But when it finally happens, it will be one of the most dramatic events in the future history of our cosmic neighborhood. Most of the small galaxies orbiting the Andromeda Galaxy are known as dwarf galaxies. These are galaxies that are much smaller and contain far fewer stars than giant galaxies like Andromeda or the Milky Way. While Andromeda holds about 1 trillion stars, many dwarf galaxies contain only a few million to a few billion stars. That may sound huge, but compared to Andromeda, it's like comparing a small village to a massive city. Because they are smaller, dwarf galaxies are also more vulnerable to the powerful gravity of larger galaxies. As they orbit Andromeda, they can slowly lose stars and gas over time. Even though they are smaller, dwarf galaxies are still fascinating systems with their own star clusters, possible planets, and long histories stretching back billions of years. When smaller galaxies are pulled apart by the gravity of the Andromeda Galaxy, the stars that escape often form long, thin streams stretching across space. These are called stellar streams. Instead of spreading randomly, the stripped stars tend to follow the path that the smaller galaxy once traveled. This creates huge ribbons of stars that can extend tens of thousands of light years across Andromeda's outer halo. Imagine pulling apart a piece of cotton candy. As you stretch it, the strands become long and thin. Stellar streams form in a somewhat similar way when gravity stretches a dwarf galaxy and pulls its stars into long trails. Astronomers can detect these streams with powerful telescopes, and they act like cosmic fingerprints, revealing which smaller galaxies were slowly torn apart and absorbed by Andromeda over billions of years. Without dark matter, the Andromeda Galaxy might not be able to stay together. The visible matter, stars, gas, and dust, does not contain enough mass to create the strong gravity needed to hold the galaxy in its current structure. Astronomers discovered that stars in the outer parts of Andromeda move much faster than expected. If only visible matter existed, those fast-moving stars would likely fly out into space, escaping the galaxy's gravity. Dark matter provides the missing gravitational pull that keeps everything bound together. You can think of it like an invisible framework or skeleton holding the galaxy in shape. Imagine spinning a giant merry-go-round. Without strong supports, pieces would fly off. Dark matter acts like the hidden support system that keeps Andromeda stable while billions of stars orbit through space. Scientists believe that most of the Andromeda Galaxy's total mass is actually dark matter, not stars, gas, or dust. In fact, the visible parts of the galaxy may make up only a small fraction of its overall mass. This means the bright spiral arms, glowing star clusters, and massive clouds of gas that we see are just the tip of the iceberg. The majority of the galaxy exists in an invisible form that can only be detected through its gravitational effects. To picture this, imagine a huge iceberg floating in the ocean. The small part above the water is easy to see, but most of the iceberg lies hidden beneath the surface. Andromeda is similar. Its visible stars are only a small part of a much larger structure. Without this massive amount of dark matter, the galaxy would likely lose stars and fall apart over time. Over billions of years, the Andromeda Galaxy and the Milky Way will eventually merge into a single giant galaxy. Instead of one quick crash, the process will happen slowly as gravity pulls the two galaxies through several close passes. During each pass, the galaxies will stretch and mix more and more. Their spiral arms will twist together, and stars will gradually settle into new orbits inside the growing combined galaxy. You can imagine this like two swirling clouds of smoke, slowly blending together. At first, they remain separate, but over time they mix until they become one larger cloud. Even though each galaxy contains hundreds of billions or trillions of stars, most of them will not collide directly. Space between stars is incredibly vast. In the end, both galaxies will lose their original shapes and form an entirely new galaxy. One major reason stars rarely collide during galaxy mergers is the enormous distance between them. Even in crowded regions of galaxies like the Andromeda Galaxy, stars are still extremely far apart. For example, the nearest star to our Sun is about 4.2 light-years away. That distance is so huge that if the Sun were the size of a golf ball, the nearest star would be roughly hundreds of kilometers away. Because of these vast gaps, galaxies are mostly empty space. When two galaxies merge, their stars pass through each other like two ghostly clouds drifting together, rather than like solid objects crashing. The real interactions happen between gravitational forces and gas clouds, which can collide and trigger new star formation. But the stars themselves usually continue traveling through space without ever touching another star. In the far future, as the Andromeda Galaxy continues approaching the Milky Way, it may appear larger in the sky than the Moon. Right now, the Moon looks big to us because it is relatively close to Earth, about 384,000 kilometers away. Even though Andromeda is vastly larger than the Moon, its extreme distance makes it look tiny today. But as the two galaxies move closer, over billions of years, Andromeda's enormous size will become more noticeable. Because the galaxy is about 220,000 light-years wide, its glowing disk could eventually stretch across a huge area of the sky. Imagine seeing a faint galaxy spread across the sky several times wider than the Moon's disk, with a bright core and wide spiral arms glowing softly in the darkness. For anyone witnessing it, the night sky would look completely different from what we see today. If intelligent civilizations exist in the far future, they might witness one of the most spectacular skies imaginable during the merger between the Andromeda Galaxy and the Milky Way. As the galaxies interact, the sky could fill with enormous glowing structures, bright star clusters, long stellar streams, and the distorted shapes of two galaxies blending together. Regions of space may shine with newly formed stars, while tidal streams stretch across the heavens. Imagine looking up and seeing entire galaxies reshaping themselves across the sky, with glowing arcs of stars slowly shifting over millions of years. Even though these changes would happen very slowly, future observers could watch the sky transform over many generations. Compared to the calm night sky we see today, the sky during this cosmic event could look dramatically more dynamic and filled with brilliant celestial structures. During the merger between the Andromeda Galaxy and the Milky Way, many new star clusters will form. These clusters are groups of stars that are born together from the same collapsing cloud of gas and dust. When huge gas clouds collide and compress during the merger, large regions of material can collapse at once. Instead of forming just one star, these dense clouds can create hundreds or even thousands of stars in the same place. Imagine a fireworks burst in the sky where many sparks appear at the same moment. Star clusters form in a somewhat similar way, with many young stars igniting together inside the same glowing cloud. These clusters will often shine brightly with young blue stars, making them easy to spot across the merging galaxy. Over millions of years, gravity keeps these stars loosely connected as they travel through space together. After the Andromeda Galaxy and the Milky Way fully merge, the final galaxy will most likely become an elliptical galaxy, rather than a spiral galaxy. Today, both galaxies have beautiful spiral arms that spin around their centers, but during the merger, the complex gravitational interactions will scramble the orderly motion of stars. Instead of moving in neat spiral patterns, stars will begin orbiting in many different directions. Over time, this chaotic motion causes the galaxy to settle into a more rounded or oval-shaped structure, known as an elliptical galaxy. Imagine stirring two spiral patterns together until the shapes blur into a single smooth cloud. The clear spiral arms disappear, leaving a large glowing cluster of stars. The final galaxy could contain trillions of stars, forming a massive elliptical system that dominates our local region of the universe. The gravitational waves produced when the black holes of the Andromeda Galaxy and the Milky Way merge will travel outward as ripples in space-time itself. Space-time is the invisible fabric that makes up the universe. Everything, stars, planets, and galaxies, exists within it. When extremely massive objects move or collide, they can disturb this fabric and send waves through it. A simple way to imagine this is to picture a large rubber sheet, stretched tight. If you drop a heavy ball onto it, the sheet bends and ripples outward. Gravitational waves behave in a similar way, except the ripples travel through the universe itself. These waves move at the speed of light, crossing enormous distances across space. Even though they spread through the universe, by the time they reach distant regions, the ripples become extremely tiny and difficult to detect. When the supermassive black holes from the Andromeda Galaxy and the Milky Way merge, some stars near the center of the new galaxy may be flung far outward into space. As the two black holes spiral around each other before merging, their powerful gravity creates a chaotic environment. Stars that pass close to this pair can experience an intense gravitational slingshot effect. This works a bit like a spacecraft using a planet's gravity to gain speed. The star can swing around the black holes and get launched outward at tremendous velocity. Some of these stars could be sent racing through the galaxy at millions of kilometers per hour, and a few might even escape the galaxy entirely. These runaway stars become cosmic travelers, drifting through space far from the crowded center where they once orbited. The Andromeda Galaxy did not form all at once. Instead, its current structure is the result of billions of years of mergers with smaller galaxies. In the early universe, galaxies were much smaller and more chaotic. Over time, gravity caused them to collide and merge with one another. Each time Andromeda absorbed a smaller galaxy, it gained more stars, gas, and dark matter. You can imagine this process like building a large snowball by rolling it through fresh snow. As the snowball moves, it collects more material and gradually becomes bigger and bigger. The same thing happened with Andromeda. Over billions of years, it slowly grew into a massive galaxy, containing around 1 trillion stars. These ancient mergers shaped its structure, created stellar streams, and helped build the giant galaxy we observe today. The Andromeda Galaxy is not unique when it comes to absorbing smaller galaxies. In fact, most large galaxies in the universe grow through similar mergers. Galactic cannibalism is simply part of how galaxies evolve over billions of years. Throughout cosmic history, gravity has constantly pulled galaxies together. Smaller galaxies are especially vulnerable because they cannot resist the powerful gravitational pull of larger ones like Andromeda. You can imagine the universe as a vast ocean where currents slowly carry objects together. Over time, smaller structures combine into larger ones. Andromeda has followed this same pattern. By absorbing dwarf galaxies and merging with neighbors, it gradually became one of the largest galaxies in our local cosmic region. This process is still happening today, and it will continue in the future, eventually leading to Andromeda's giant merger with the Milky Way. Over billions of years, the powerful gravity of the Andromeda Galaxy may eventually pull in and absorb many of the smaller galaxies in the local group. These dwarf galaxies slowly orbit around Andromeda, but their paths can gradually change because of gravitational interactions. As time passes, some of them may drift closer to the giant galaxy. Once they get too close, Andromeda's gravity can begin pulling them apart. Their stars spread out into long streams and eventually mix into Andromeda's halo and disk. You can imagine this like small streams flowing into a massive river. At first, they remain separate, but eventually the water blends together. Through this slow process, Andromeda could continue growing larger over cosmic time, adding the stars of many smaller galaxies to its already enormous population. The enormous mass of the Andromeda Galaxy gives it a powerful gravitational influence over nearby galaxies in the local group, because Andromeda contains around 1 trillion stars, along with huge amounts of dark matter. Its gravity reaches far into surrounding space. This gravitational pull affects how smaller galaxies move, orbit, and sometimes even merge with it. You can think of Andromeda like a giant planet in space, with many moons, except the moons are actually entire dwarf galaxies. These smaller galaxies slowly travel around Andromeda under its gravitational control. Some of these galaxies will continue orbiting for billions of years, while others may eventually drift too close and get pulled apart. Through this powerful gravitational influence, Andromeda helps shape the structure and motion of many galaxies in our cosmic neighborhood. Some binary star systems in the Andromeda Galaxy produce extremely intense radiation. This happens when one of the stars in the pair is a very dense object, such as a neutron star or a black hole. In these systems, the powerful gravity of the dense object can pull gas from its companion star. The gas spirals inward and forms a hot disk of material. As the gas falls deeper into the strong gravitational field, it becomes incredibly hot, sometimes reaching millions of degrees. At these extreme temperatures, the gas begins to release powerful radiation, including X-rays that can travel across millions of light years. You can imagine this like a cosmic furnace, where matter gets pulled in and heated until it glows with tremendous energy. These energetic systems help astronomers locate hidden neutron stars and black holes inside Andromeda. Some neutron stars in the Andromeda Galaxy emit powerful pulses of radiation as they spin. These special neutron stars are called pulsars. When a massive star collapses into a neutron star, the remaining object can spin extremely fast, sometimes many times every second. At the same time, Strong magnetic fields around the neutron star focus beams of radiation out into space. As the neutron star spins, these beams sweep across space like the rotating beam of a lighthouse. If one of those beams happens to point toward Earth during each rotation, astronomers detect it as a repeating pulse of radiation. Some pulsars spin so quickly that they can produce hundreds of pulses every second. Even from millions of light years away, these steady signals can be detected with powerful instruments, allowing astronomers to study the behavior of neutron stars inside the Andromeda Galaxy. Many planets in the Andromeda Galaxy may orbit red dwarf stars, which are small, cool stars that are extremely common in the universe. Red dwarfs are much smaller than our Sun. Some have only 10 to 20% of the Sun's mass. Because they burn their fuel very slowly, these stars can shine for trillions of years, far longer than stars like our Sun. Planets around red dwarfs often orbit very close to their stars in order to receive enough warmth. Even though the star is dimmer, a nearby planet could still have temperatures that allow liquid water to exist. You can imagine a small red dwarf star glowing softly like a cosmic ember, with planets circling closely around it. Since red dwarfs are so common, many planetary systems in Andromeda may look very different from our solar system, yet still contain interesting and potentially habitable worlds. Even though the Andromeda Galaxy may contain trillions of planets, scientists currently have no direct evidence that life exists there. The main reason is distance. Andromeda is about 2.5 million light-years away, which makes detailed observation extremely difficult. Even our most powerful telescopes struggle to study individual stars in that galaxy, let alone detect life on planets orbiting them. Imagine trying to determine whether a tiny island on the other side of the planet has animals living on it, while viewing it only through a very distant telescope. That gives an idea of how challenging this task is. For now, astronomers can only study the galaxy itself and estimate how many stars and planets might exist there. While the possibility of life in Andromeda remains fascinating, it remains one of the great unanswered questions of the universe. The Andromeda Galaxy lies about 2.5 million light-years away from Earth. A light-year is the distance light travels in 1 year, and light moves incredibly fast, about 300,000 kilometers per second. That means light could circle the Earth more than 7 times in a single second. Now imagine that speed continuing non-stop for an entire year. That enormous distance is just 1 light-year. Andromeda is 2.5 million of those distances away. Another way to picture this: if you could travel to Andromeda in a jet airplane flying about 900 kilometers per h, the journey would take well over 2 billion years. That's longer than complex life has existed on Earth. Yet even across this unimaginable distance, Andromeda is still considered our cosmic neighbor. In the scale of the universe, where galaxies can be billions of light-years apart, 2.5 million light-years is actually relatively close. The Andromeda Galaxy is about 220,000 light-years wide, making it an enormous structure in space. A light-year, remember, is the distance light travels in a full year at incredible speed. When you multiply that distance by 220,000, you begin to see how truly massive Andromeda is. To picture this, imagine traveling across the galaxy at the speed of light, the fastest speed possible in the universe. Even at that unbelievable speed, it would still take 220,000 years just to cross from one side of Andromeda to the other. If the galaxy were scaled down to the size of a large city, our entire solar system would be smaller than a tiny grain of sand somewhere inside it. This vast width contains spiral arms, star clusters, gas clouds, and billions upon billions of stars spread across an immense cosmic disk. When Persian astronomer Abd al-Rahman al-Sufi observed the Andromeda Galaxy in the year 964, he described it as a small cloud. This description actually makes perfect sense when you consider how Andromeda appears to the naked eye. Without a telescope, Andromeda does not look like a galaxy at all. Instead, it appears as a tiny, faint, blurry patch of light in the night sky. It resembles a thin smudge or a soft cloud glowing very gently among the stars. Imagine looking up at the sky and seeing what looks like a small puff of mist that never moves. That's exactly what early observers saw. What makes this amazing is that the small cloud he described was not a cloud at all. It was actually the combined light of around 1 trillion stars, all so far away that they blur together into a faint glowing patch. The discovery that Andromeda is a separate galaxy completely transformed astronomy. Before this moment, the universe seemed relatively small, with the Milky Way believed to contain everything that existed. But once scientists realized Andromeda was its own galaxy millions of light years away, the scale of the universe suddenly became almost unimaginably large. It meant the cosmos was not made of just one galaxy, but countless galaxies spread across vast distances. Each of these galaxies could contain hundreds of billions or even trillions of stars. To picture this shift, imagine thinking there is only one island in the entire ocean, and then discovering that the ocean is actually filled with millions of islands scattered everywhere. This single realization opened the door to modern cosmology. It showed that the universe is far bigger, more complex, and more mysterious than anyone had previously believed. The spiral arms of the Andromeda Galaxy are packed with dust and regions where new stars are constantly being born. These areas are known as star-forming regions, where huge clouds of gas and dust slowly collapse under gravity to create new stars. Think of these regions like cosmic nurseries. Inside them, clouds many times larger than our entire solar system slowly squeeze together. As the gas compresses, temperatures rise until new stars ignite. These spiral arms stretch across tens of thousands of light years and contain enormous clouds that can form thousands or even millions of stars at once. If you could fly through one of these regions, you would see glowing clouds, young bright stars, and powerful radiation lighting up the surrounding dust. It would look like a gigantic glowing fog filled with newborn stars scattered across the galaxy. The halo surrounding the Andromeda Galaxy contains many ancient star clusters that formed extremely long ago. These clusters are groups of stars that were born together from the same cloud of gas and have stayed bound by gravity ever since. Many of these clusters are more than 10 billion years old, meaning they formed when the universe itself was still young. That makes them older than our Sun by several billion years. Imagine a group of stars that have been traveling together through space since before Earth even existed. These clusters act like cosmic fossils, preserving clues about the early days of the galaxy. They are usually found far from the bright center of the galaxy, floating in the vast halo like tiny islands of ancient stars, scattered in a dark ocean of space. By studying them, astronomers can learn about the earliest stages of galaxy formation. Some stars in the Andromeda Galaxy are billions of years older than our Sun. While the Sun formed about 4.6 billion years ago, many stars in Andromeda were already shining long before our solar system even existed. These ancient stars may be 10 to 12 billion years old, meaning they formed when the universe itself was still relatively young. At that time, galaxies were still growing, merging, and shaping themselves into the forms we see today. Imagine a star that was already shining for billions of years before Earth formed. By the time dinosaurs appeared, those stars had already lived through most of their long lives. These old stars act like cosmic historians. By studying their composition and age, astronomers can learn what the universe was like in its early days, when the first generations of stars began lighting up the cosmos. New stars are still forming inside the Andromeda Galaxy today. Even though the galaxy is billions of years old, it is far from finished creating stars. Large clouds of gas and dust scattered throughout the galaxy slowly collapse under gravity, giving birth to fresh stars. These star-forming regions can be enormous. Some clouds are so large that they could create thousands of stars at once. When new stars ignite inside these clouds, they light up the surrounding gas, making those regions glow brightly. You can think of Andromeda like a cosmic city that never stops building new lights. While many older stars continue aging, new ones keep appearing in different parts of the galaxy. This ongoing star formation means Andromeda is still active and evolving, constantly reshaping itself as new generations of stars are born across its spiral arms. The supermassive black hole at the center of the Andromeda Galaxy is incredibly massive. Astronomers estimate that it weighs about 100 million times the mass of our Sun. To picture how extreme this is, imagine squeezing the mass of 100 million suns into a region of space smaller than our solar system. The gravity in such a place would be unbelievably strong. If something drifted too close, like a star or a cloud of gas, the black hole's gravity could pull it inward at incredible speed. As the material falls in, it heats up and can release huge amounts of energy before disappearing beyond the black hole's boundary. Even though the black hole itself is invisible, its massive gravity acts like a cosmic anchor, controlling the movement of stars in the crowded central region of the galaxy. The two bright star clusters near the center of the Andromeda Galaxy orbit, extremely close to the galaxy's supermassive black hole. This region is one of the most intense environments in the entire galaxy. Because the black hole's gravity is so strong, stars in these clusters move at incredible speeds as they circle the center. Imagine cars racing around a tiny circular track at extreme speed. That gives a rough idea of how these stars behave. The distance between these stars and the black hole is very small compared to the rest of the galaxy. In cosmic terms, they are packed tightly together in the crowded central region. Studying how these clusters orbit helps astronomers understand the powerful gravitational forces near the black hole and how stars survive in such an extreme part of the galaxy. The small satellite galaxies around the Andromeda Galaxy orbit it much like moons orbit a planet. Gravity from Andromeda's enormous mass pulls these smaller galaxies into long, slow paths through space. Some of these galaxies travel hundreds of thousands of light years away from Andromeda, yet they are still trapped by its gravitational pull. Their orbits can take billions of years to complete, slowly circling the giant galaxy. To imagine this, think about the moon orbiting Earth. Now scale that idea up enormously. Instead of a moon and a planet, picture entire galaxies orbiting another galaxy. As these smaller galaxies move around Andromeda, gravity can stretch and distort them. Over time, some of them will drift closer and eventually be pulled apart and absorbed, adding their stars to Andromeda's growing structure. Some of the smaller satellite galaxies orbiting the Andromeda Galaxy may eventually merge with it completely. Over extremely long periods of time, gravity slowly pulls these dwarf galaxies closer and closer to the giant galaxy. As they move inward, the strong gravitational forces of Andromeda can begin tearing them apart. Their stars get stretched out and gradually absorbed into Andromeda's disk or halo. This process can take hundreds of millions or even billions of years. But eventually, the smaller galaxy may disappear entirely as its stars become part of Andromeda. You can imagine this like a small stream flowing into a large river. At first, the stream is separate, but eventually the water mixes completely with the larger flow. Through these mergers, Andromeda slowly grows bigger and more massive over cosmic time. The invisible mass inside the Andromeda Galaxy is believed to be something called dark matter. Dark matter does not shine, reflect light, or produce any glow that telescopes can see, yet its gravity clearly affects how galaxies behave. Astronomers realized dark matter must exist when they measured how stars move inside galaxies like Andromeda. The stars were moving far too fast to be held together by the gravity of visible matter alone. It's similar to watching a merry-go-round spinning extremely fast. If the central support were weak, everything would fly apart. But in Andromeda, something unseen is providing extra gravity to keep the galaxy stable. Although scientists cannot see dark matter directly, they estimate that it may make up most of the galaxy's total mass, quietly shaping the structure and motion of Andromeda. When astronomers measured the speed of stars in the outer regions of the Andromeda Galaxy, they discovered something puzzling. Those stars were moving much faster than gravity from visible matter alone should allow. Normally, objects farther from the center of a galaxy should move more slowly, just like the outer planets in our solar system take longer to orbit the Sun. But in Andromeda, stars near the edges of the galaxy are still racing around at very high speeds. Imagine spinning a rope with a small weight tied to the end. If the rope were weak, the weight would fly off. In the same way, those fast-moving stars should escape the galaxy's gravity. But they don't. Something unseen is holding them in place. This strange behavior became one of the strongest clues that dark matter must exist throughout the galaxy. Astronomers estimate that the Andromeda Galaxy and the Milky Way will begin interacting in about 4 billion years. Right now, the galaxies are still far apart, but their mutual gravity is slowly pulling them toward each other. Over billions of years, the distance between them will gradually shrink. Eventually, their outer regions will start to feel each other's gravitational pull. This will cause both galaxies to stretch, twist, and distort long before their centers come close. To imagine this timescale, consider that Earth itself is about 4.5 billion years old. That means the first major stage of this cosmic encounter will happen roughly as far in the future as Earth's entire history so far. So even though Andromeda is racing toward us through space, the process unfolds extremely slowly on human timescales. When the Andromeda Galaxy and the Milky Way finally merge, the new galaxy is often nicknamed Milkomeda. The name simply combines Milky Way and Andromeda. This future galaxy will contain the stars, gas, and dark matter from both original galaxies. Altogether, it could hold trillions of stars, making it far larger than either galaxy on its own today. Imagine taking two enormous spinning storms and blending them together into a single, even larger storm. That is somewhat similar to how the two galaxies will combine over billions of years. Milkomeda will likely look very different from the spiral galaxies we see today. Instead of clear spiral arms, the final galaxy may appear more smooth and rounded, with stars moving in many different directions. It will become the dominant galaxy in our cosmic neighborhood. As the Andromeda Galaxy continues approaching the Milky Way, it will also become much brighter in our night sky. This happens because the closer an object is, the more of its light reaches us. Right now, Andromeda appears as a faint, misty patch that is difficult to see unless the sky is very dark. But as the distance between the two galaxies slowly shrinks over millions of years, its light will appear stronger and clearer. Imagine a distant city at night. From far away you might see only a faint glow, but as you drive closer, the lights become brighter and more detailed. The same will happen with Andromeda. Its glowing center and vast star-filled disk will gradually become more visible, turning what is now a tiny smudge in the sky into a much brighter and more impressive sight. As the Andromeda Galaxy and the Milky Way begin interacting, the shape of our own galaxy will start to distort and stretch under the powerful gravitational forces between them. The Milky Way is currently a spiral galaxy with well-defined arms, but when Andromeda gets close enough, gravity will begin pulling on different parts of the Milky Way unevenly. This will stretch the spiral arms and pull stars into long streams. Imagine two spinning storms slowly pulling at each other's edges. Their shapes begin to twist and stretch as they get closer. Over time, the neat spiral pattern of the Milky Way will start to break apart. Stars, gas, and dust will shift into new paths, and some material will be pulled far away from the galaxy. This is one of the first visible signs that the two giant galaxies are beginning their long merger. When the huge gas clouds of the Andromeda Galaxy and the Milky Way collide, they can trigger powerful bursts of star formation. Astronomers call this a starburst, when stars begin forming much faster than normal. Under ordinary conditions, stars form slowly over long periods of time, but when gas clouds crash into each other during a galaxy merger, the gas gets compressed and squeezed together. This pressure causes large regions of gas to collapse quickly. Imagine squeezing a sponge full of water. When you apply pressure, everything inside gets pushed closer together. In galaxies, this squeezing helps gas clouds collapse and ignite new stars. During these starburst periods, galaxies can create thousands or even millions of new stars in a relatively short cosmic time, lighting up large areas with bright young stars. During the merger of the Andromeda Galaxy and the Milky Way, enormous streams of stars will stretch across space. These streams form when gravity pulls stars away from their original positions and spreads them along long paths. Instead of staying inside the spiral arms of their original galaxies, these stars will drift into extended arcs that trace the motion of the galaxies during the merger. Some of these streams could stretch hundreds of thousands of light years long, creating glowing ribbons of stars across the merging system. Imagine two swirling clouds of glitter being slowly pulled apart. The glitter would stretch into long, sparkling trails between them. Stellar streams form in a similar way when gravity stretches groups of stars into huge cosmic ribbons. These streams will remain visible for millions or even billions of years, marking the history of the galaxy's interaction. As the two supermassive black holes from the Andromeda Galaxy and the Milky Way move closer together, they will eventually form a binary black hole system. This means the two black holes will orbit around each other, locked together by their enormous gravity. Instead of merging immediately, they will first circle each other like two extremely massive dancers, spinning around a shared center. Each orbit will slowly shrink as energy is lost through gravitational interactions with surrounding stars and gas. To imagine the scale of this system, remember that each black hole contains millions to hundreds of millions of times the mass of the Sun. Their combined gravity will strongly affect the stars near the center of the new galaxy. Over time, the orbit will tighten more and more. Eventually, the two black holes will come so close that they will finally merge into a single, even larger black hole. After the supermassive black holes of the Andromeda Galaxy and the Milky Way merge, the result will be an even larger black hole at the center of the newly formed galaxy. The Milky Way's central black hole contains about 4 million times the mass of the Sun, while Andromeda's black hole is much larger, at around 100 million solar masses. When they combine, the new black hole will contain most of that combined mass, making it one of the most massive black holes in our local region of the universe. Imagine merging two enormous mountains into a single, even taller mountain. The new structure becomes the dominant feature in the landscape. In the same way, this merged black hole will become the gravitational heart of the new galaxy, influencing the motion of stars and gas across the central region for billions of years to come. Astronomers have found strong evidence that the Andromeda Galaxy absorbed smaller galaxies in the past, and this evidence appears in the form of stellar streams. These stellar streams are long trails of stars, stretching across Andromeda's halo. They formed when smaller galaxies were pulled apart by Andromeda's powerful gravity. As the dwarf galaxy broke apart, its stars spread out along the path it once traveled. You can imagine this like breadcrumbs scattered along a trail. Even if the original object is gone, the trail it left behind still tells the story of where it once moved. Some of these streams extend tens of thousands of light years across space, acting like cosmic fingerprints of ancient collisions. By studying these streams, astronomers can reconstruct the history of past galaxy mergers that helped build the Andromeda Galaxy over billions of years. The disk of the Andromeda Galaxy still shows scars left behind by past interactions with smaller galaxies. These scars appear as distortions, ripples, and unusual structures within the galaxy's disk. When a smaller galaxy passes through or near a larger one, its gravity can disturb the stars and gas inside the bigger galaxy. The result is similar to dropping a stone into calm water, where ripples spread outward across the surface. In Andromeda, these ripples can stretch across tens of thousands of light years, slightly bending or warping parts of the galaxy's disk. Astronomers study these distortions carefully because they reveal evidence of past encounters with dwarf galaxies. Each ripple or warped structure acts like a fossil record of a past collision, helping scientists understand how Andromeda evolved over billions of years. The local group, the region of space that includes the Andromeda Galaxy and the Milky Way, contains more than 50 known galaxies. These galaxies are all loosely bound together by gravity and slowly moving through space as a group. Most of these galaxies are dwarf galaxies, meaning they are much smaller than giant galaxies like Andromeda. Some may contain only a few million stars, while Andromeda alone contains about 1 trillion stars. You can imagine the local group like a cosmic neighborhood. Andromeda and the Milky Way are the two largest houses, while dozens of much smaller houses surround them. Even though these galaxies are separated by huge distances, often hundreds of thousands or millions of light years, gravity still connects them, slowly shaping their motions over billions of years. One of the dwarf galaxies currently being absorbed by the Milky Way is called the Sagittarius Dwarf Galaxy. This small galaxy orbits around our own and is slowly being pulled apart by the Milky Way's gravity. As Sagittarius moves through the Milky Way, strong gravitational forces stretch it out. Its stars are gradually being stripped away and spread across the sky in long stellar streams that wrap around our galaxy. Imagine a small cloud drifting too close to a powerful storm. The storm begins tearing the cloud apart, scattering pieces across the sky. A similar process is happening to the Sagittarius Dwarf Galaxy. These streams of stars are so large that they extend tens of thousands of light years across space. By studying them, astronomers can see how the Milky Way slowly grows by absorbing smaller galaxies. Some of the powerful X-ray sources in the Andromeda Galaxy come from neutron stars pulling material from nearby companion stars. A neutron star is the incredibly dense remnant left behind after a massive star explodes. As a supernova, even though it may be only about 20 kilometers across, it can contain more mass than our Sun. That means a teaspoon of neutron star material would weigh billions of tons on Earth. In some star systems, a neutron star orbits close to another normal star. The intense gravity of the neutron star can pull gas away from its companion. As this gas spirals inward, it heats up to millions of degrees and produces strong X-rays. You can imagine this process like a cosmic whirlpool, where gas gets pulled inward and heated until it shines with powerful energy. Inside the Andromeda Galaxy, there are regions where stars are forming very actively. These areas contain huge clouds of gas and dust, but are slowly collapsing under gravity to create new stars. When a large cloud of gas becomes dense enough, parts of it begin to collapse inward. As the gas compresses, it heats up until nuclear fusion begins, and a new star is born. Some of these star-forming regions can stretch hundreds of light years across and may produce thousands of stars at once. You can imagine these areas as cosmic nurseries, where new stars are constantly being created inside glowing clouds. Many of these regions appear bright in telescope images because young stars release strong energy that lights up the surrounding gas, making entire sections of the galaxy glow. Even though the Andromeda Galaxy may contain trillions of planets, detecting them is extremely difficult because of the enormous distance between us and the galaxy. Most planets discovered by astronomers are located inside our own Milky Way, and even those are often hundreds or thousands of light years away. Detecting planets in Andromeda is far harder because it sits about 2.5 million light years from Earth. At that distance, individual stars themselves appear very small and faint. Trying to detect a planet around one of those stars is like trying to spot a tiny insect flying next to a distant lighthouse from thousands of kilometers away. Because of this challenge, astronomers must rely on very advanced techniques and powerful telescopes. Even then, confirming planets in Andromeda remains extremely rare and difficult. Not every planet in the Andromeda Galaxy orbits a star. Some planets may be rogue planets, meaning they drift through space completely alone. These planets likely formed in normal planetary systems, but were later ejected by powerful gravitational interactions. For example, when large planets shift their orbits, or when stars pass close to each other, smaller planets can be thrown out of their systems. Once ejected, these planets wander through interstellar space without a parent star to orbit. You can imagine them like cosmic travelers, drifting through a dark ocean of space, with no sun to warm them. Even without a star, some rogue planets might still contain internal heat from their formation or radioactive elements, possibly keeping subsurface oceans warm beneath thick layers of ice. In a galaxy with trillions of planets, many could be roaming alone like this. The Andromeda Galaxy is also known by another name used by astronomers, Messier 31, often shortened to M31. This name comes from a famous catalogue of objects in the night sky created by the French astronomer Charles Messier in the 1700s. Messier was actually searching for comets, but he kept seeing fuzzy objects that did not move like comets. To avoid confusing them, he made a list of these objects. Each one received a number in what became known as the Messier catalogue. Andromeda was the 31st object on that list, which is why astronomers call it M31. Think of it like a library system for the sky. Instead of book numbers, each object gets a catalogue number, so astronomers around the world know exactly what they're talking about. So when scientists say M31, they're simply using the official catalogue name for the Andromeda Galaxy. Most galaxies in the universe are moving away from us because space itself is expanding. But the Andromeda Galaxy is one of the rare exceptions. Instead of drifting away, Andromeda is actually moving toward the Milky Way. This happens because the two galaxies are close enough for their gravitational pull to overcome the expansion of the universe. In simple terms, their enormous masses are pulling them toward each other like two giant magnets in space. Imagine two massive whirlpools in a cosmic ocean, slowly drifting closer together. Over billions of years, gravity steadily brings them nearer and nearer. Right now, the distance between the Milky Way and Andromeda is about 2.5 million light years. But that gap is slowly shrinking. Far in the future, these two giant galaxies will eventually meet and merge, creating an entirely new galaxy. In the 1920s, astronomer Edwin Hubble made a discovery that completely changed how we understand the universe. Using a powerful telescope at Mount Wilson Observatory, he studied the faint spiral object known as the Andromeda Nebula. Hubble noticed special stars inside it, called Cepheid variable stars. These stars brighten and dim in a predictable way, which allows astronomers to calculate how far away they are. When Hubble measured them, he realized something shocking. Andromeda was far too distant to be inside the Milky Way. Instead, it was millions of light years away, far beyond the boundaries of our galaxy. This meant the mysterious spiral object was not a nebula at all, but an entire galaxy of its own. It was like suddenly realizing that a faint island on the horizon is not a small hill, but an entire continent. In the night sky, the Andromeda Galaxy appears as a small, fuzzy patch of light located within the constellation Andromeda. Constellations are patterns of stars that people long ago used to map and navigate the sky, much like landmarks on a map. If you find the Andromeda constellation, the galaxy sits quietly among those stars as a faint, misty glow. To the naked eye, it does not look like a spiral galaxy with arms and structure. Instead, it resembles a soft blur almost like someone lightly brushed a tiny bit of chalk across the dark sky. This faint patch is actually the combined glow of roughly 1 trillion stars, all so far away that they blend together. It's similar to looking at a distant city at night, from hundreds of kilometers away. The individual lights disappear, leaving only a dim, glowing haze. At the center of the Andromeda Galaxy lies a large rounded region called the central bulge, and it is packed with very old stars. These stars formed billions of years ago, long before our sun even existed. If you could travel to the middle of Andromeda, the sky would look incredibly crowded. Instead of seeing scattered stars like we do from Earth, the sky might glow with thousands of bright stars visible at once, much closer together than in our part of the Milky Way. This bulge is also brighter than the rest of the galaxy, because so many stars are packed tightly into that region. Imagine the difference between a quiet countryside and the center of a huge city at night, filled with lights. That's similar to the contrast between the outer galaxy and its glowing central bulge. These ancient stars help astronomers understand the early history of the galaxy. Some of the globular star clusters found around the Andromeda Galaxy may actually be older than the Milky Way itself. These clusters formed extremely early in the history of the universe, possibly more than 12 billion years ago. To put that into perspective, the Sun is about 4.6 billion years old, which means these clusters could be more than twice as old as our solar system. They were already shining long before Earth even formed. These ancient clusters are like cosmic time capsules. Inside them are stars that have remained together for nearly the entire history of the universe. By studying them, astronomers can learn what the early universe was like when galaxies were just beginning to form. Imagine a group of stars that started shining when the universe was still young and have been traveling together through space for billions of years. Many of the massive stars in the Andromeda Galaxy burn much hotter and faster than our Sun. These stars contain far more mass, which creates intense pressure and temperature inside their cores. As a result, their nuclear fuel is consumed extremely quickly. Our Sun is expected to live for about 10 billion years, slowly burning its hydrogen fuel. But some massive stars may burn through their fuel in only a few million years. That's like a candle that burns thousands of times brighter, but lasts only a tiny fraction as long. Because these stars shine so intensely, they often appear bright blue or white and can outshine many smaller stars around them. Their short lives also lead to dramatic endings. When their fuel runs out, many of them explode in powerful supernova explosions, spreading heavy elements across the galaxy. Not all stars in the Andromeda Galaxy are giant and short-lived. In fact, many of them are tiny red dwarf stars, which are some of the smallest and longest-lasting stars in the universe. Red dwarfs are much smaller and cooler than our Sun. Some have only 10 to 20% of the Sun's mass, making them more like cosmic embers compared to the Sun's blazing furnace. Because they burn their fuel extremely slowly, they can live for trillions of years. To understand how long that is, the universe itself is only about 13.8 billion years old, which means many red dwarfs will outlive the current age of the universe many times over. In Andromeda, countless red dwarfs quietly shine for unimaginable lengths of time, acting like steady cosmic candles that may still be glowing long after many larger stars have disappeared. The enormous black hole of the Andromeda Galaxy sits deep inside the galaxy's dense central core. This region is packed with huge numbers of stars crowded very close together compared to the outer parts of the galaxy. If our solar system were located near this galactic center, the night sky would look completely different. Instead of seeing scattered stars like we do from Earth, the sky might be filled with thousands of bright stars glowing all around, much like standing in the middle of a city surrounded by lights. In the middle of this crowded region lies the invisible black hole. Although it cannot be seen directly, its gravity strongly affects the nearby stars. Astronomers discovered its presence by observing how these stars move extremely fast around the center, as if they are orbiting something incredibly massive hidden in the core. Supermassive black holes, like the one in the Andromeda Galaxy, play an important role in shaping how galaxies grow and evolve. Even though they sit in the center and occupy a tiny part of the galaxy's total size, their influence can extend much farther. When gas and dust fall toward a black hole, enormous amounts of energy can be released. This energy can heat surrounding gas or push it away from the center. In some cases, powerful streams of energy called jets shoot outward from the region around the black hole. These processes can affect how new stars form in the galaxy. If too much gas is pushed away or heated, star formation can slow down. You can think of the central black hole as a cosmic regulator, helping control the flow of gas and energy that shapes the long-term development of the galaxy. Another well-known satellite galaxy orbiting the Andromeda Galaxy is M110. Like M32, M110 is a dwarf galaxy, meaning it is much smaller than Andromeda, but still contains an enormous number of stars. M110 holds several billion stars, all bound together by gravity. From a distance, it appears as a faint oval-shaped glow near Andromeda when viewed through a telescope. Despite being smaller, M110 still plays a role in the cosmic environment around Andromeda. Over long periods of time, gravity between the two galaxies influences their shapes and motion. You can think of M110 as a small companion traveling alongside a giant, slowly orbiting Andromeda through space. These interactions between large galaxies and their smaller companions are common across the universe and help galaxies grow over billions of years. Some stars that once belonged to smaller galaxies orbiting the Andromeda Galaxy have already been absorbed into Andromeda itself. Over billions of years, gravity slowly pulls stars away from these dwarf galaxies and spreads them into Andromeda's outer regions. When this happens, the stars no longer remain part of their original galaxy. Instead, they become part of Andromeda's halo or outer disk, mixing with the stars that already existed there. You can imagine this like raindrops falling into a large lake. At first, the drops come from separate clouds, but once they land in the lake, they become part of the same body of water. Astronomers can sometimes identify these captured stars because their motion and chemical composition are slightly different, revealing that they once belonged to another galaxy long ago. The dark matter halo surrounding the Andromeda Galaxy stretches far beyond the visible disk of stars. While the bright spiral structure is already enormous, the invisible halo surrounding it is even larger. Astronomers believe this halo extends hundreds of thousands of light years into space, possibly reaching distances several times wider than the galaxy's glowing disk. In other words, the part of Andromeda we can see is only the central portion of a much bigger structure. Imagine a small glowing lantern inside a giant invisible sphere. The lantern is easy to see, but the much larger sphere around it is hidden. This extended halo also affects objects far from the galaxy's center. Small satellite galaxies, gas clouds, and stars in the outer regions all move under the influence of this enormous invisible gravitational field. Without this vast halo, Andromeda would behave very differently. The Andromeda Galaxy has played an important role in helping scientists understand how galaxies move and behave. By studying the motion of its stars, gas, and satellite galaxies, astronomers gained valuable clues about the forces shaping large galaxies. When researchers mapped the rotation of Andromeda, they noticed that its stars did not behave the way simple models predicted. The outer stars moved much faster than expected, which hinted that something invisible was influencing the galaxy's gravity. By analyzing these movements, scientists began developing better theories about galactic dynamics, which is the study of how galaxies rotate, interact, and evolve over time. You can think of Andromeda as a natural laboratory in space. Because it is relatively close to us, compared to other large galaxies, astronomers can observe it in detail and learn how giant galaxies grow and move across billions of years. As the Andromeda Galaxy and the Milky Way get closer to each other, their powerful gravity will begin to distort both galaxies. Instead of remaining neat spiral shapes, their structures will slowly stretch and twist. This happens because gravity pulls more strongly on the parts of each galaxy that are closer to the other. Over time, the spiral arms will begin to stretch outward, and stars will start shifting into new paths. You can imagine this like two swirling storms, slowly pulling at each other's edges. The closer they get, the more their shapes change. These distortions will create long streams of stars and gas stretching across space. The once clear spiral patterns will gradually become more chaotic as both galaxies begin the long process of merging. This transformation will take hundreds of millions to billions of years to fully unfold. Even though the Andromeda Galaxy and the Milky Way will eventually merge, direct collisions between individual stars are actually very unlikely. This might sound surprising because each galaxy contains hundreds of billions or even trillions of stars. But space inside galaxies is incredibly vast. The average distance between stars is so large that they usually pass by each other without touching. To imagine this, picture two swarms of tiny bees flying through a massive stadium. Even if the swarms cross paths, the bees have so much open space that almost none of them will collide. In the same way, when the two galaxies merge, most stars will simply move into new orbits around the combined galaxy. The real interactions happen between gas clouds and gravitational forces, not direct star crashes. As the Andromeda Galaxy moves closer to the Milky Way over billions of years, its structure will eventually become detailed enough that its spiral arms may be visible to the naked eye. Today, Andromeda appears only as a faint blur because it is extremely far away. Even though it is huge, the details of its spiral arms are too distant for our eyes to see without telescopes. But as the galaxy approaches, the view will slowly improve. The bright central core will grow larger, and the sweeping spiral arms filled with stars and glowing gas clouds could become visible across the sky. Imagine looking up and seeing a giant spiral pattern of stars slowly stretching across the night, almost like a massive cosmic hurricane frozen in space. For future observers, the night sky could transform into one of the most spectacular cosmic views imaginable. During the long merger between the Andromeda Galaxy and the Milky Way, the night sky could eventually be filled with overlapping star fields from both galaxies. Right now, the stars we see mostly belong to our own galaxy, but as the two galaxies move through each other, stars from Andromeda will begin appearing in the same regions of the sky as Milky Way stars. Imagine two massive clouds of glowing fireflies drifting into each other. At first, the groups are separate, but eventually they mix together until you can't easily tell which firefly came from which cloud. The same thing will happen with stars. From certain places in the merging galaxies, the sky could appear densely filled with stars from two giant galaxies mixed together, creating an incredibly bright and crowded view of the universe. Many of the massive stars formed during the merger of the Andromeda Galaxy and the Milky Way will live very short but dramatic lives. Because these stars are extremely large, they burn their nuclear fuel at an incredible rate. While our sun will shine steadily for about 10 billion years, some massive stars may live for only a few million years before their fuel runs out. In cosmic terms, that is a very short lifespan. You can think of it like a huge bonfire compared to a small candle. The bonfire burns brighter and hotter, but it also burns through its fuel much faster. When these massive stars reach the end of their lives, many will explode in powerful supernova explosions, sending shockwaves and heavy elements across space, and helping create the next generation of stars. While some stars will be thrown outward during the merger of the Andromeda Galaxy and the Milky Way, others will move closer toward the center of the newly forming galaxy. The powerful gravitational forces during the merger will constantly reshape the paths of stars. As the two galaxies mix together, many stars will be pulled into new orbits that gradually bring them toward the central region. You can imagine this like stirring two large clouds of particles together. Some particles scatter outward, while others slowly settle toward the middle. In galaxies, gravity acts like the force doing the stirring. Over time, the movement of stars begins to settle into a more stable structure. Many stars that once belonged to the outer parts of the original galaxies may end up orbiting closer to the center of the merged galaxy. This process helps reshape the structure of the final galaxy. When the two supermassive black holes from the Andromeda Galaxy and the Milky Way finally merge, they will release enormous gravitational waves. These waves are ripples that travel through space-time itself, spreading outward across the universe. Gravitational waves were predicted by Albert Einstein in his theory of relativity. They behave somewhat like the ripples that spread across water when a stone is dropped into a pond. But instead of water, the ripples move through the very fabric of space and time. During the final moments of the black hole merger, the energy released will be tremendous. For a brief time, the event could release more power than all the stars in the universe combined. These waves will travel outward at the speed of light, carrying the signal of this enormous cosmic event across millions of light years. When the supermassive black holes from the Andromeda Galaxy and the Milky Way merge, the event will reshape the central region of the new galaxy. As the two black holes spiral closer together, their intense gravity will strongly affect nearby stars. Some stars may be pulled into new orbits, while others may be flung outward at high speeds. Imagine two powerful whirlpools in water merging into a single larger whirlpool. The water around them would swirl and shift dramatically. In a similar way, the gravity of the merging black holes will stir the stars near the galaxy's center. Once the black holes finally combine, the new, larger black hole will dominate the central region. Its gravity will organize the surrounding stars into new paths, creating a completely reshaped galactic core that will remain stable for billions of years. Not every star inside the Andromeda Galaxy originally formed there. Some stars now orbiting Andromeda were actually born in completely different galaxies. When Andromeda absorbed smaller dwarf galaxies in the past, many of their stars were pulled away and scattered into Andromeda's halo and outer regions. Over time, these captured stars became part of the larger galaxy. It's similar to how people from different towns may move into a large city and eventually become part of its population. Even though they live in the city now, they originally came from somewhere else. Astronomers can sometimes identify these stars because their chemical composition and motion are slightly different from stars that formed inside Andromeda itself. These foreign stars act like cosmic immigrants, carrying clues about the smaller galaxies that Andromeda consumed billions of years ago. The process where a large galaxy absorbs smaller galaxies is often called galactic cannibalism. The Andromeda Galaxy has experienced this process many times throughout its history. When a dwarf galaxy drifts too close to a giant galaxy like Andromeda, gravity begins pulling it apart. Over time, its stars spread out and eventually become part of the larger galaxy. This might sound dramatic, but it is actually very common in the universe. Many large galaxies grow by slowly capturing and absorbing smaller ones. You can imagine it like a large river swallowing smaller streams. At first, the streams are separate, but eventually their water becomes part of the main river. Through galactic cannibalism, Andromeda has gradually grown larger and more massive, collecting stars from many smaller galaxies over billions of years. The galaxies in the local group, including the Andromeda Galaxy and the Milky Way, are held together by gravity. Even though these galaxies are separated by huge distances, their combined gravitational pull keeps them connected as a group. Some galaxies in the local group are millions of light years apart, yet gravity still influences how they move through space. Over extremely long periods of time, this gravitational attraction slowly changes their paths. You can imagine this like a group of dancers connected by invisible strings. Even if they move around the floor, the strings gently guide their motion. Because of gravity, Many of the smaller dwarf galaxies orbit around the larger ones. Over billions of years, some of them may drift closer and eventually merge with bigger galaxies, like Andromeda or the Milky Way. Gravity quietly shapes the entire structure of this cosmic neighborhood. The Andromeda Galaxy sits close to the center of the local group, the small cluster of galaxies that includes the Milky Way and more than 50 other galaxies. Because Andromeda is extremely massive, holding around 1 trillion stars, its gravity plays a major role in shaping the movement of galaxies in this region. Many of the smaller dwarf galaxies orbit around either Andromeda or the Milky Way. You can imagine the local group like a large system with 2 major centers of gravity, similar to 2 large magnets, influencing nearby objects. Those 2 gravitational centers are Andromeda and the Milky Way. Even though the galaxies in this group are separated by millions of light years, their gravitational pull still affects how they drift through space over billions of years. Andromeda's central position helps make it one of the most influential galaxies in our cosmic neighborhood. The Andromeda Galaxy contains many binary star systems, where 2 stars orbit around each other instead of existing alone like our Sun. In a binary system, the 2 stars are held together by gravity and travel around a shared center point. Some pairs orbit each other slowly over many years, while others complete an orbit in just a few days. You can imagine this like 2 dancers, holding hands and spinning around together. Both stars move in a coordinated motion as they circle their common center. Binary systems are actually very common throughout the universe. In fact, many astronomers believe that a large portion of stars may have at least one stellar partner. In galaxies like Andromeda, these systems can lead to fascinating events. Interactions between the 2 stars can produce X-rays, stellar explosions, or unusual stellar behavior. Some stars in the Andromeda Galaxy eventually collapse into incredibly dense objects called neutron stars. This happens after a massive star reaches the end of its life and explodes as a supernova. During the explosion, the outer layers of the star blast outward into space, but the core of the star collapses under its own gravity. The matter inside becomes compressed so tightly that protons and electrons combine to form neutrons, creating a neutron star. Even though a neutron star may be only about 20 kilometers across, it can contain more mass than our entire Sun. That means a tiny amount of its material would weigh billions of tons on Earth. These extreme objects spin rapidly and can produce powerful radiation, making them some of the most fascinating remnants of dead stars in galaxies like Andromeda. Some of the planets that may exist in the Andromeda Galaxy could be Earth-like worlds. These would be rocky planets with solid surfaces, similar in size and composition to Earth. In our own Milky Way, astronomers have already discovered many rocky planets orbiting distant stars. Some of them lie within the habitable zone, the region around a star where temperatures might allow liquid water to exist. If similar planetary systems exist in Andromeda, and there is no reason to think they wouldn't, then some planets there could also have oceans, atmospheres, and stable temperatures. Imagine a planet orbiting a distant star in Andromeda, with blue oceans, clouds drifting through the sky, and landscapes shaped by wind and water. Although we currently have no direct evidence of such planets, the enormous number of stars in Andromeda makes it very possible that Earth-like worlds exist there. With trillions of possible planets in the Andromeda Galaxy, scientists believe that life could theoretically exist there. Wherever planets have the right conditions, such as liquid water, stable temperatures, and a protective atmosphere, life might be able to develop. On Earth, life appeared relatively quickly once conditions became suitable. Microbial life existed here more than 3.5 billion years ago, showing that life can emerge under the right circumstances. If similar environments exist on some of the countless planets in Andromeda, it's possible that life could arise there as well. You can imagine distant oceans on a planet orbiting a star in Andromeda, perhaps with alien ecosystems evolving beneath unfamiliar skies. However, even if life does exist there, the immense distance between our galaxies makes it extremely difficult for us to detect or study it directly.